The last algorithm that we're going to learn how to solve a traveling salesman problem is called the cheapest link algorithm. Now again, this one is not in your textbook, but this one can also solve traveling salesman problems, and it's a nice change of pace from what we've been doing with the nearest neighbor stuff. So here's the algorithm steps for cheapest link. Now the first thing you're going to do is you're going to represent the problem with a complete weighted graph. Right, so for step 2, you are going to mark the edge of least weight wherever it is in the graph. So this is kind of like a holistic search. You're going to look over the entire weighted graph, and wherever that least weighted edge is, you're going to mark it. Now, if there was ever a case that you have 2 weights, or 2 of those least weights on different edges, at that point in time you would just pick one of them. Okay, so then for step 3, you're going to pick or mark the next edge of least weight. Again, wherever it is. Could be on the complete opposite side of the graph as this first edge that you marked. You don't care. Now, for these 2 first edges, you kind of get for free, meaning that for every edge we want to grab after that, we're going to have some restrictions. So for step 4, continue marking the next edge of least weight unless it violates one of these below 2 rules. So here's the 3-edge rule. The 3-edge rule says that so maybe I'll put this in a different color, you cannot have 3 edges out of a vertex. Okay, so if the edge that you're about to grab would cause this, you have to skip it. Partial circuit rule says you cannot create a circuit too early. Basically means you can't create a circuit until you're at the very, very end of this algorithm when you're ready to kind of close up your graph. So you can't create a big circuit and you can't create any little baby circuits. We're going to see this in our next example. Okay, so you can continue grabbing any edge unless it violates one of these 2 rules. So assuming that it doesn't violate any of these rules, you're going to then keep running through this until you get to the step that you can connect the vertices that will close the circuit. And actually, if you were just to keep running through this algorithm, you would naturally see this. Okay, but we're going to talk about a shortcut that lets you know when you're ready to close. And then for step 6, then, you're going to write the circuit from the specified starting vertex. So we're going to take into that account all the way at the end. Now there's a lot going on here, so let's take a look at all of this inside of our example. There is an unmanned mission to explore the moons in our solar system. The shuttle is scheduled to leave and return to Earth. The graph shows the time in years required for travel between any two moons, as well as between any moon and Earth. Find the cheapest link tour and give the total time for this tour. So notice on this problem, the weights represent years, so I'm trying to minimize time, not necessarily money in this case. Now, as part of this algorithm, when it says the shuttle is scheduled to leave and return to Earth, that's going to be the specified starting vertex. We'll deal with this at the end. We're not going to worry about that as part of this cheapest link algorithm. So, the algorithm says then you would have a complete weighted graph, which we have represented here. And then you're going to pick the cheapest edge wherever it is, or the edge of least total weight. So looking at this entire graph, looking at all these different numbers, what is the smallest number that you see for any of the weights? This looks like this 0.6 right here, right? So we're going to mark it, and I'm going to record it. Okay, so where it says then on this one, when you're going to do this, you're going to list the weights in the order found. So the smallest weight that I'm seeing anywhere in the graph is 0.6. We're going to deal with actually writing the tour all the way at the end as well. So right now we're just going to deal with the weights. Now the next least weight anywhere in the graph would be where? Looks like this 0.8 all the way out here. So I'm going to record that one as well. Now the first two edges you get for free, meaning you don't have to worry about that 3-edge rule or the partial circuit rule. But from here on out we're going to have to think about that anytime we grab an edge. So after 0.8, what is going to be the next lowest number that you see? So we're running through here, it looks like it would be this 1.1. Now if I were to grab it, do I create 3 edges coming out of a vertex? Nope. And if I were to grab it, do I create a circuit? No. So I could go ahead and grab it, and then I'm going to list it over here. Now what would be the next lowest number after that? Looks like it would be this 1.5 over here. But that's going to be a problem. Notice if you were to mark it, you would have this little tiny circuit over here. So I'm not going to be able to grab that number. So what I'll do instead is I like to cross it off. If you want, you can write yourself a note that this one was violated because of the partial circuit rule, but otherwise I just cross it so that way I don't just get distracted by it later. Because here's the thing, when you're running through this algorithm, if there was a weight that you were supposed to grab, but you didn't see it, then you're pretty much going to have to redo the algorithm all the way back from the beginning. Okay, so I like to cross that off to remind myself I thought about it and I rejected it because it was going to make a circuit over here. Alright, so what's the next lowest number after this 1.5? So looking at the rest of the numbers, looks like this 3.1 might be my winner. Okay, so if I were to grab it, do I create a circuit? No, because I'm going to mark it right here, and I don't create a circuit where I would just kind of dink around between a couple different vertices, and I don't have 3 edges coming out of any vertex. So that one's going to work, and I'll record it. Now the next lowest number after that would be this 3.2, but that one's going to be a problem, because if I were to grab it, I would create this little circuit right here. So I'm not going to be able to grab that one. Next lowest number after 3.2, looks like this 4.7, oh nope, actually this 3.6 right here. But if I were to grab it, I would have 3 edges coming out of IO. So that violates that 3-edge rule, so I can't have the 3.6. I'll kick him out. Next one after the 3.6 was this 4.7 I saw up here, but that one's also a problem. That would create 3 edges out of IO, so that one's out as well. Next lowest number after 4.7 is a 5.1. That's a problem as well. That would be 3 edges out of here. After that one, it looks like it would be this 5.2. That wouldn't be a problem. I would have 3 edges out of here. Next one would be this, looks like 5.6. It's a problem, 3 edges out of here. Next one after that would be the 5.7. Let's see, that one might work. I wouldn't get 3 edges out of either one of these vertices, and if I were to connect it, did I create a circuit anywhere? Nope, I didn't. So there would be no way to kind of close this up. So I would have the 5.7, that's the next one I'm going to grab. Now at this point in time, you could keep running through this algorithm, and it will tell you which edges that you would want to grab, but we've kind of hit a critical point in the solution process. So I want you to note this graph has n equals 6 vertices. So the final tour, or that final circuit I would be looking for, will have 6 edges. At this point in time, I've already grabbed 1, 2, 3, 4, 5 edges. So I don't have much choice right here. I'm going to have to grab the edge to close this circuit. So that's kind of what's going on with this step 5. Connect the vertices that will close the circuit. So right here I've kind of hit this very special point. So let's see here. What edge would I have to grab to kind of close this whole thing up? So if I were to bounce around right here, I'd be like right here, over, down, up, here. It'd be this edge right here, with a weight of 8.1. Okay, so then that closes then my circuit. Let's go ahead and find the overall weight for this circuit. So adding up all these numbers, we get an overall weight of 19.4, and this would be years, would be my units. So I'm not tracking money. Again, in this problem, I'm tracking time. And then finally for step 6, we'll go ahead and write the circuit from the specified starting vertex. Here's now where I'm going to take into account that I'm leaving from Earth. So from Earth, where could I go? Now I could go to Titan or to Callisto. Now this one would take longer, so maybe in terms of a real life scenario, especially if I'm maybe trying to get pictures back from these places, maybe we'll go to the closer one first. Okay, but either one of them would have been a viable option. So from Earth, we'll go to Callisto, then to Io, down here to Ganymede, over to Mimas, to Titan, and then finally the trek home to Earth. So this would be the circuit, and also as a reminder, I would accept the mirror image of this one. So maybe I'll just write or mirror image. Either one of them would be a viable option with an overall weight of 19.4 years. And then as a reminder, when you go to run this algorithm, I will require that you list the weights in the order found. And I want you to notice, because of the nature of what the algorithm is saying, that these weights will always be in ascending order.